Thanks for having me. So this is a talk based on work with Nabil Iqbal, and it's about, as Joe said, analogies between zero-form symmetries and one-form symmetries. And let me start by describing some of my own motivation for thinking about this. There may be lots of other reasons for thinking about it, which is an attempt to enlarge the Landau paradigm to include higher form symmetries. So the Landau paradigm is, of course, the basis of most of our understanding of condensed matter. And it's the idea that phases of matter can be understood by and classified by how they represent their symmetries. And moreover, at a critical point, the critical degrees of freedom should be fluctuations of the order parameter that breaks the symmetries. And a sort of an important corollary of this is that if there are gapless excitations or degeneracies in a phase, then they should arise as Goldstone modes for spontaneously broken symmetries. They should be swept out by broken symmetries. Landau-Ginzburg theory is a particular weaponization of this point of view, that it's extremely useful for finding representative states, for figuring out the gross phase structure, and in high enough dimensions, even quantitatively describing phase transitions. So this paradigm is has really taken a beating in the last 20 years or so, because there are some important apparent exceptions to it, which have gotten a lot of attention. So in particular, phases that are distinguished from a trivial phase not by any local order parameter. So that is the phenomenon of topological order, which happens, say, in fractional quantum Hall states and in gap spin liquids, for example. And more generally, anytime there's a deconfined state of a gauge theory, so such as the Coulomb phase of Maxwell theory. And so it's important to recognize that if we enlarge our understanding of what a symmetry is, then we can also enlarge this Landau paradigm. And a particular goal of this work is to understand how to generalize the idea of Landau-Ginzburg theory. Okay, so let me complement Davide's review of one-form symmetries by talking about the case of continuous symmetries, which is I think a little easier to understand. So a continuous zero-form symmetry comes with a conserved current, which of course means that we can make a conserved charge by integrating it over a codimension 1 slice of spacetime, and that's okay. Sorry, something happened. And that the value of this charge won't change unless we pass through a charged operator. And in the case of a zero-form symmetry, a charged operator is a local operator. Okay, so a one-form symmetry is very similar, except the current is a two-form, and which means that its Hodge dual is something we can integrate over a codimension 2 slice of spacetime. So here I've drawn a one-dimensional thing in 3 dimensions. And the fact that the current is conserved means that the value of this charge only depends on the topological class of this surface, and only changes when it passes through a charged operator. And in the case of a one-form symmetry, a charged operator is a loop operator, and it transforms under the symmetry by acquiring a phase, which is the line integral over the loop of some closed one form. Okay, so some physics examples where one-form symmetries appear. I think probably the most basic example is the 3D Ising model, which has a Z2 one-form symmetry. And the strings that can't break in that case are the domain walls separating the regions of upspins and downspins. And the charged line operator is the disorder operator. And then the example Davide mentioned is the center symmetry of a gauge theory that doesn't have minimally charged matter, where the charged operator is the Wilson line in the minimal representation. And then another example, which will be important for my talk, is Maxwell theory, with electric charges but no magnetic charge, where the fact that magnetic field lines can't end can be expressed as this conservation law, and the charge operator in that case is the 't Hooft line. Okay, so a reason to care about this formal development is that anything you can do with ordinary symmetries, you can also do with higher form symmetries. So in particular, they can be spontaneously broken or not. Just as a zero-form symmetry is spontaneously broken if a charge operator has long range correlations, one-form symmetry is spontaneously broken if the charge operator, which in this case is a loop, if its expectation value doesn't fall off as we make the loop large. So by doesn't fall off, I mean a perimeter law. And a perimeter law is the same as not falling off because we can set this coefficient to 1 by local counterterms along the loop. So there is some loop. So if this happens, there is some loop operator we can define, which has a non-zero expectation value. And this is a very fruitful idea for many reasons. One of which is that we can interpret topological order as spontaneous breaking of such a discrete one-form symmetry. So in particular, one way to diagnose topological order is the presence of degenerate vacua, which are distinguished from each other not by any, where you get from one to the other, not by the action of any local operator, but by the action of some extended operator winding around the space. And the set of such extended operators generate a higher form symmetry group. And the statement that such an operator takes one vacuum to the other is the statement that the ground state spontaneously breaks that symmetry. So it's actually sort of even a sort of tautological statement. And as Davide also mentioned, we can understand the gaplessness of the photon as a consequence of a generalization of Goldstone's theorem. This idea has had many other important applications. I think probably the most important of which is the kind of application that Davide mentioned, namely that if we have more symmetries, there can be more anomalies, and anomalies are precious because they're renormalization group invariant information that allows us to understand what's allowed to happen in the infrared given the high energy physics. Okay, so now having talked about analogies, ways in which one form symmetries are analogous to zero form symmetries, I have to mention a place where that analogy actually breaks down. And that's that we're used to the idea that if we have an emergent symmetry, what high energy physicists call accidental symmetry, that the consequences of that symmetry are only approximate. So in particular, if I have a spontaneously broken continuous symmetry, and we explicitly break it, say by adding some irrelevant operators to the action that violate that symmetry, then the Goldstone bosons get a mass. Right? So the consequences of this approximate symmetry will be only approximate. And so now I just said that we can understand the gaplessness of the photon as a consequence of a Goldstone theorem for spontaneous breaking of some one-form symmetry, which is a symmetry because of the absence of magnetic monopoles. So does that mean that if there exists some arbitrarily heavy magnetic monopole, whose existence explicitly breaks this conservation law, does that mean that the photon should get a mass? And perhaps surprisingly, the answer to this question is no. And one way to see that is by dimensional analysis. The mass of the photon has to go to 0 when the monopole mass goes to infinity, and there's no way to do that with using just the monopole mass. A better argument for this is what happens if we put the theory on a circle. So in that case, the monopole world lengths can wind around the circle, and they act as monopole instantons. And as Polyakov showed us, the photon gets a mass from that gas of monopole instantons, which goes like e to the minus the monopole mass times the radius of the circle, and this goes to 0 when the radius of the circle goes back to infinity. And I guess it's worth mentioning that there's a discrete analog of this statement about the robustness of one form of spontaneously broken one form symmetries, namely in the phase diagram of discrete gauge theory. There's a special point, which in this picture is here, which is the Tora code, which is a model where the one form symmetries are exact, and they're also spontaneously broken. But everywhere else in the deconfined phase, which is this region here, the one form symmetries are not exact. They're explicitly broken by the Hamiltonian, but there is nevertheless an emergent one form symmetry which is spontaneously broken. But nevertheless, the topological ground state degeneracy is exact in the thermodynamic limit. Okay, so maybe it's worth mentioning that known forms of topological order in fewer than 4+1 dimensions, in 3+1 dimensions or fewer, have the property that they're unstable to being put at finite temperature, so that any finite temperature instantly destroys the phase. And that's the same fact I was just mentioning. If you put the theory on a circle, the one form symmetry becomes a mass is generated for the photon, and so it's smoothly connected to infinite temperature. So maybe it's worth mentioning, to see the pattern here, it's worth mentioning that there are stable topological orders in 4+1 dimensions, namely two-form gauge theory is a phase where the topological properties survive below some critical temperature. And in the U1 version of that, U1 two-form gauge theory, there's a massless photon mode in a range of finite temperatures. And that's because a theory with a two-form symmetry and a circle still has a one-form symmetry. Okay, so there's a third explanation for this phenomenon that one sometimes hears, namely that the operators that are charged under a one-form symmetry are loop operators, which, loop operators aren't local, and so we can't add non-local operators to the action at all, and therefore the symmetry can't be broken. This argument is not entirely satisfying because, for example, on the lattice, the action is already a sum of loop operators, and the real question is, some ensemble of loops. And the real question is, as we coarse grain to get to the infrared, what happens to this ensemble of loops? Now, as some precedent for how to think about this question, let's think about the case of a zero-form symmetry. Let's think about perturbing, say, a CFT by some charged operator with some definite dimension. So one way to diagnose its effect on the infrared physics is just by doing conformal perturbation theory, compute the change in the partition function resulting from this perturbation, and ask whether it produces an infrared singularity. So L is the system size here, and precisely when the operator is relevant, there's an infrared singular contribution. And so that's one way to diagnose the effect of such a thing. But notice that if the operator had an expectation value in a CFT, of course it can't. But if it did have an expectation value, then the perturbation of the perturbation would always be infrared singular. There would be a contribution proportional to the VEV, which is always infrared singular. So that's related to the statement that if a zero-form symmetry is only approximate, then its consequences are only approximate. So let's try to understand the analog of that for one-form symmetries. So let's think about a theory that has a one-form symmetry, and let's start in the broken phase, where there's a perimeter law for this loop operator, and perturb the action by some ensemble of these loop operators, and ask what happens in perturbation theory. So to make progress, I'm going to make some assumptions. First, I'm going to regulate this sum on the lattice. I'm going to assume a strict perimeter law so that this expectation value is precisely t to the length of the loop, some parameter t. And I'm going to approximate the loops as independent from each other, just so I can calculate. And so with those assumptions, we can calculate this sum over loops of expectation values, and the answer looks like this. And so we see that when t is smaller than some critical value, the sum over loops converges. Above, when t becomes large enough, the sum over loops diverges. And near the critical point, it takes this familiar form. It's exactly the form of the world line description of a Higgs particle. And so we know very well when such a thing will produce a mass for the photon, namely if the charged particle condenses, the photon will be massive, and otherwise it won't. So only when this t becomes large enough does it actually have any effect on the infrared physics. So the slogan that I'd like to extract from this is that what it means for a loop operator to be relevant, I'm not sure if relevant is exactly the right word to use here, but what it means for a loop operator to have a singular effect on the infrared physics is that a charged particle condenses. So it's actually this sounds very fancy, but it's actually a pretty familiar thing. Okay, so with that, let me return to the main line of development here and introduce this what we call mean string field theory. And it's the answer to this analogy, namely zero-form symmetry is to Landau-Ginzburg theory or mean field theory, as one-form symmetry is to what? And so to answer that question, let me briefly give you a sort of Wilsonian reminder of a way to think about Landau-Ginzburg theory. So based on this Landau principle, the degrees of freedom should be swept out by the symmetries. And so let's assume that there's an order parameter which transforms linearly into the symmetry. Let's talk about a zero-form U1 symmetry for definiteness. And this order parameter is some coarse-grained object. This thing that we're trying to develop is some long wavelength description of the physics where we've, phi is averaged over some microscopic blocks. And what can the action for this thing be but a sum of all local symmetric terms organized by a derivative expansion with the higher derivative terms suppressed by the length scale over which we averaged. Okay, so that leads to this familiar form of the action. And so let's just work by analogy. So this order parameter is a function from the space of points to a linear representation of G. So that is something that transforms like this, where G is the symmetry group. And the analog of that for one form symmetry is some functional from the space of loops to a linear representation of G, which is exactly this field that's charged under a one-form symmetry, transformed by this phase determined by the line integral of a closed one form. To write kinetic terms, we need derivatives, which compare, in the zero form case, compare nearby points in space. And the analog of that is the area derivative, which compares the value of the field at nearby loops. Right, so this is a loop that differs from this big loop by adding a little plaquette. To write the action, we need to integrate, and the analog of that is this now a functional integral over loops. And of course, it's always a good idea, given the symmetry, to couple to background gauge fields, which is usually accomplished by promoting this derivative to a covariant derivative. And in the one-form case, we can promote this area derivative to a covariant area derivative. Okay, so with that, we can follow the same logic and just write down all terms consistent with these basic principles in an area derivative expansion. And so the action inevitably takes the form of a path integral over loops of, there can be a term which is local in loop space, which is just a function of the square of the field. It's just the square so that it's invariant under the one-form symmetry, and this function we can in turn, this should be a capital V, we can expand in some polynomial in powers of the field. And then there can be a kinetic term made from these area derivatives. And then the surprise, perhaps, is that there's another kind of term which is allowed, which is a term that changes the number of loops. It's not local in loop space, but rather it's an integral. The simplest one is an integral over three curves, which are forced to meet in the following way. So namely, that one of them is equal to the sum of the other two as integration domains. And if that property is met, then this product of the fields is invariant under the one-form symmetry. The phases cancel out. And so this is also this and its generalization to more fields is a term that respects the symmetry of the problem. But moreover, it actually is local. Although it's not local in loop space, it is local in ordinary space because it involves only a single integral over the center of mass of the strings. Okay, so good. So this is the theory we're going to study a little bit. And to get started, let's think about the case when this potential, so this coefficient in the potential is the analog of the thing that tunes us through the phase transition of the ordinary theory. And so let's think about the case when that's positive, and then we can ignore the higher order terms. And so the potential looks like this. And in that case, the field wants to be as small as possible. It can't actually be zero because we have to put a boundary condition on small loops, where the field is not zero. And instead, the solution is of this form. It's an area law with at large loops, it's an area law with a coefficient with a tension which is square root of this parameter r. So now we can ask what happens when this r becomes negative. Obviously, this solution is no longer correct. When r becomes negative, the potential looks like this. The field wants to condense. So in particular, when the loops are large, the field approaches this expectation value determined by the location of the minimum of the potential. The strings want to condense. And if we study fluctuations about this solution, there's a special fluctuation, which is a slowly varying one-form symmetry transformation parameterized by this field A mu. And if we plug this back into the action, do some path integrals, the result is exactly a Maxwell term for this special mode, and all of the other modes are massive. And so this mode is manifestly a Goldstone mode since it arose from a slowly varying symmetry transformation, and the gauge coupling, the Maxwell coupling, is determined by the superfluid stiffness, right? That is the width of the minimum of this potential. Okay, and moreover, the current, the one-form current evaluated on the solution takes exactly the form that we'd expect from what I said earlier about Maxwell theory. Okay, so far I've been talking about a U1 one-form symmetry because it's simple to work in the continuum. But with the same framework, we can also describe a discrete one-form symmetry by explicitly breaking the U1 symmetry down to a ZP subgroup by adding a term like this. And if we start in the broken phase and add this term, it's not too hard to see that adding no other ingredients, it reduces to an effective description of ZP gauge theory, which is a good description of a state that spontaneously breaks a ZP1 form symmetry. Okay, so in the remaining however many minutes, I want to say something about phase transitions. Okay, so if we were to ignore this recombination term, so that 5 minutes left. Okay, if we were to ignore this recombination term, for example, if there were some psi goes to minus psi symmetry, I don't know how that would arise. Then this theory would predict a continuous mean field transition from the broken phase to the unbroken phase, with an exponent for the tension, which is 1/2, which you'll notice is very different from the value that people observe in numerics in say 3 space-time dimensions. And maybe that's not too surprising, because dimensional analysis says that the upper critical dimension, where this, above which this mean field theory should be a quantitative description of the phase transition, is 8, which is interesting partly because the same value for the upper critical dimension was obtained by Parisi using an estimate for the fractal dimension of random surfaces. Okay, but we shouldn't ignore this recombination term. And you see that this recombination term is cubic in the order parameter. And so the fact that this mean field theory allows a cubic term suggests that the transition should generically be first order, which is actually what people see when they simulate deconfinement transitions in above 3 dimensions. I think this actually provides something like an appealing explanation for this fact. But I have to mention that 4 dimensions, the 3 + 1 dimensions, is special. So the action, the 2 important parameters in the action are the coefficient of the side of the 4th term and the coefficient of the recombination term. And notice that their engineering dimensions are both 4 when d = 4. And why is that? Well, so there are 2 possible notions of lower critical dimension that one might have, and these 2 notions coincide in the case of zero form symmetries. So one of them is the dimension below which fluctuations forbid symmetry breaking. So that's 2 dimensions for continuous zero form symmetries, but for one form symmetries that's actually in 3 dimensions, as these people showed. But the second notion of lower critical dimension, sorry, this should be an L, is where the linearly transforming fields become dimensionless. So again, that's in 2 dimensions for zero form symmetries, but that's in 4 dimensions for one form symmetries. And so this offers an interesting possibility, namely that there can be a Kosterlitz-Thouless-like transition in 4 dimensions. So let me remind you what that entails in the zero form case. So a zero form U1 symmetry in 1 + 1 dimensions has an order parameter that has naive dimension 0, and its phase therefore has logarithmic correlations. And so there's a line of fixed points parameterized by this coupling constant G, which terminates when some charge operator becomes relevant at some universal value of this coupling. So the analog of that for one form symmetries is in 3 + 1 dimensions, where our string field has naive dimension 0, but its phase is the photon field, which has these power law correlations, the familiar propagator of the photon. And so there's a line of free fixed points described by Maxwell theory, which we can expect to terminate when some loop operator becomes relevant, or at least somehow dramatically affects the infrared physics. And so what might we mean by the dimension of a loop operator? I think a good definition is to use conformal symmetry and think about a straight line operator, and define use the notion of scaling dimension in terms of the operator product expansion with the stress tensor, right? The OP of the stress tensor, which with an operator has a term which is proportional to the dimension of the operator. And so another way to think about that is we compute the expectation value of the stress tensor in the presence of this line operator. It has a term which we can interpret as its dimension. Okay, so the dimension. So now let's think about this Kosterlitz-Thouless-like transition in 4 dimensions. So let's start with the U1 symmetric theory and perturb it by this term that breaks it to a ZP1 form symmetry. This perturbation, this coupling constant has a dimension which is proportional to G² P², where P is the order of the group to which we break it. And for a large enough P, this dimension passes through 4 at some critical value of the coupling. So that, as the coupling looks something like this, and here's this is G in turn is determined by R, it's determined by the radius of the potential. So very deep in the broken phase, the coupling is very small, and as we get closer and closer to the would-be ordinary transition, at some point that's superseded by the fact that this coupling passes through passes through a value such that this operator becomes relevant. And so here's a picture of the potential as a vary R perturbed by this side of the p term. You can see deep in the ordered phase, you can't see the corrugations at all. But as you get closer to the transition, the corrugations become more and more important, and you can see the fact that there's only a ZP symmetry. And in fact, this is exactly what happens in simulations of ZP lattice gauge theory in 3+1 dimensions. So this parameter is essentially R, and this parameter is P, the order of the group. For small p, there's just a first order transition from a confined phase to a deconfined phase. But for large enough p, there's an intermediate Coulomb phase, which is the same as what you would get if you simulated U1 gauge theory. Okay, and so this leads to a beautiful universal prediction, which I guess I have to point out was also made by Carty in 1980 without the benefit of thinking about higher form symmetries. So the usual Kosterlitz-Thales transition comes with a universal jump in the superfluid stiffness, because the superfluid stiffness is what determines where this operator becomes relevant. And that can be measured by the response to twisted boundary conditions or in experiments. And the analog of that is a universal jump in the gauge coupling that should happen when this operator becomes relevant, which can be measured by a response to background one-form symmetry flux. So some twisted boundary conditions, which essentially amounts to measuring the capacitance. And indeed, if you we did some crude numerics, you can see that the curvature of this is proportional to the superfluid stiffness, and in the Coulomb phase it has non-zero value, and in the confining phase it jumps to 0. But as many of you are probably jumping up and down to remind me, this transition is actually weakly first order. So this transition here from the confined phase to the Coulomb phase actually is a first order transition with a very tiny latent heat. Many people have discovered this over the years. One way to see it is the fact that the stiffness fails to collapse as a function of system size. And so we're used to the idea that when a transition is first order, we should give up on asking universal questions. But if the transition is always weakly first order, then there should be a reason for that. And I think we can figure out why that is. So one reason that transitions are always weakly first order is if there's a nearby pair of complex fixed points. I think this is not quite as exciting as that. The reason that's happening here can be seen by duality. So let's think about a dual description of this U1 gauge theory, where the monopoles are described by a scalar field charged under the dual U1 gauge theory, and that monopole is becoming light near the transition. So this is just the 3+1 dimensional abelian Higgs model, and Coleman-Weinberg taught us that the fluctuations drive this to be weakly first order, and at weak coupling, it's weakly first order. So then the question we have to answer is, why should the coupling be weak? And now I need to remind you of the slogan that we figured out, which is that condensing a charged particle is the same as a loop operator becoming important in the infrared. And so if this slogan is correct, it means that the coupling at the transition is fixed by this picture. So the value of the coupling is determined by at what value of G does this loop operator have dimension 4. And if that universal, it's the fact that universal value is small that explains why the latent heat is small. It explains why the transition is always weakly first order. Okay, so that's the end of what I wanted to say. There's a lot more to understand about this mean string field theory. We've kind of just scratched the surface, and I think maybe I should emphasize that another important motivation for thinking about it is that I don't think we really understand what we mean by saying that something is a gauge theory. I mean, certainly we can construct them and understand things about them, but if someone hands you a piece of rock and asks whether it should be described by a gauge theory or not, I don't think we really have enough tools to answer that question in general. And so, I think it's important to contrast what we've done here with previous work that described gauge theory in terms of field theories in loop space. Rather than starting with a particular gauge theory and changing variables to reformulate it as a theory in loop space, we've started just by thinking about the symmetries and asking what the most generic possible effective action for such a thing is under the assumption of this generalized Landau principle, and arrived at a few slightly universal properties of gauge theory. Okay, thanks.
Okay, so we have time for some questions. So I think Ofer, you have one?
I know, I was just clapping, sorry.
Oh,
Questions
I'm
now?
sorry. I thought it was a hand raise. Sorry, I didn't mean to put you on the spot.
Hi, Ofer.
Okay, I have a question. So maybe you said this and I missed this, but for a zero form symmetry, we always learn that we can trust mean field theory for d greater than equal to 4. Is there a similar thing for one form symmetry? Is there a dimension that?
Right. Yeah. So that's what I was trying to estimate here.
Okay, I missed that.
So if we ignore this recombination term, the analog of d equals 4 is
I see.
this dimension here where this where the coupling becomes dimensionless, right? Which for the side of the fourth term is 8 dimension, and for the recombination term is 12 dimensions.
Okay, I see.
Yeah.
I see.
Is
there a similar thing you could do for like two form symmetries?
Yeah, that's right. I think you could, though. I don't think the technology is well developed, right? So just to evaluate the classical action, we had to do some path integrals, some world line path integrals, and the analog of that would be some integral over two-dimensional membranes, which I personally don't understand it nearly as well.
Okay, Marco, you have a question?
Yes, hi. What about going beyond mean field theory? Can you do perturbation theory? Is there some diagrammatics? How would it look like?
That's a very interesting question, and we have not tried yet. Yeah, so right, you might hope to try to develop some kind of epsilon expansion, for example, perhaps starting around here. We haven't done that yet. Yeah, so I don't know. It's a great question.
Alexa?
So I have a question about the conclusion slide. You mentioned you have some way of thinking about what is a gauge theory, which I think amounts to an answer like it's something that has a one-form symmetry, and so you can build a field theory in loop space. Is that right?
Well, I mean, I don't want to claim that we have a complete answer to that question, because of course there are gauge theories that don't have one-form symmetries.
Right. Okay.
Which I think is probably what you want to say.
Most of them don't, right? That's where I was going. So
yeah. So, but I think it's a step in the right direction.
Yeah, that's fair. That's fair. I just wanted to know what the claim is. Okay, thank you.
Shimon?
Sorry, you're muted.
You're muted.
What is the range of validity of this Landau-Ginzburg theory that you construct? Usually Landau-Ginzburg is valid and you get information only when you sit on the critical point and not when you go away from it.
Well, I think in the usual case, the criterion is the theory is valid as long as there aren't other degrees of freedom that are important, right? So near the critical point of a Landau phase transition, only the order parameter fluctuations matter at all.
Yeah.
And so this is the right description. But there could of course be systems where even when you go quite far from the critical point, no other degrees of freedom get involved. And so that's really the criterion.
But this is up to you to show it, that there are no other degrees of freedom that become important.
That's right. Yeah. So I think it's the same promise as for the usual theory, as for the zero form case.
Are there any other questions? Okay, if not, let's take John again.